Hey, what's up, everyone? Welcome to Stoichiometry slash Solutions Part 1, where today we're going to go over moles, molar mass, and chemical equations. And it's hard to start stoichiometry without a good understanding of the mole. And what you need to know about the mole is that it's just a number. It's Avogadro's number, and it works similar to how you would use a unit. So think about how you would use a dozen. Like if you had a dozen eggs, you could have a mole of atoms. And the reason a mole is so big is because in chemical terms, atoms are so small that you need so many of them to make something that we can fathom, right? And so the mass of one mole of a substance is called the molar mass. Usually, if you have a periodic table, the molar mass is listed under the element symbol, and I'm realizing there should be a 2 there. That's carbon, not hydrogen. Um, but yeah, 1 mole of a substance is called the molar mass. So 1 mole of carbon is 12.01 grams. The great thing about a mole is that we can use it to relate mass to particles. So if we consider this problem right here, how many carbon atoms are in 24.02 grams of carbon, it seems kind of hard to do until you realize that you can just use moles. So let's think about it. If we have grams, right, the weight, and we divide it by the molar mass of the substance, in this case carbon, we are going to get the number of moles. And with the number of moles, we can turn that into the number of particles, in this case, the number of carbon atoms, by just multiplying by Avogadro's number. And that's going to give us the number of particles. So let's see what that comes out to, right? We have 24.02 grams of carbon, and we know that the molar mass of carbon is 12.01 grams. So that means we're going to have 2 moles of carbon. And so multiplying by Avogadro's number is going to give us the number of carbon atoms in 2 moles of carbon. And that, let me get my calculator out. 2 times 6.02 times 10 to the 23rd. It's going to be about 1.20 times 10 to the 24. So we did the calculation, and it turns out that in 24.02 grams of carbon, you're going to have 1.20 times 10 to the 24th carbon atoms. And this is a powerful thing because it's hard to imagine that many particles, but you can imagine 24.02 grams of carbon. And it also gives you perspective as to the quantities of atoms and how small an atom really is. In 24.02 grams, which is really not a lot, you have an unfathomable number of atoms. Moles can also be used for certain units, and we're going to go over 2 of them. The first one being molarity, which is the moles of solute per liter of solution. So we're going to explore this more in solution stoichiometry, but I want to introduce it now. And molarity is signified with a big M right here. And it's the moles of solute over liters of solution. So if you had 1 mole of a solute over 1 liter, then you have a 1 molarity. You have a 1 molarity solution. And the next one is molality. And I don't know why they named it that. It looks basically the same. It's just 1 letter is different, but they're very different. So molality is moles of solute per kilogram of solvent, and it's signified by little m right here. So the only thing different really is that instead of liter like you had in molarity, you're going to have kilogram on the denominator. And remember that molarity is big M and then molality is small m. We'll see molality doesn't have a lot of uses. Molarity comes up a lot, but molality has a couple uses, which I think we get to in later on. And so now that we have a good idea of what a mole is and how to use it, we can start talking about chemical equations. But before we can get into chemical equations, we need to know about chemical formulas, which are just a way of representing the number and types of atoms present in a molecule. I think my thing is blocking the and there. And you've definitely seen chemical formulas before, right? Things like water, H2O, and carbon dioxide, CO2, are chemical formulas. In water, it tells you in one molecule of water, you're going to have two hydrogen atoms and one oxygen atom. And then in carbon dioxide, you have one carbon atom and two oxygen atoms. And the important thing about these is that, unless stated, the net charge of these are going to be zero. So these don't have charges. Right now, it doesn't seem very useful to know that, but it does come in handy later on. So just have that known, and just keep that in the back of your head. All right, so let's do a bit of practice, and we're asked to find how many hydrogen atoms are in 64.02 grams of NH3, ammonia. We can take a very similar approach to how we did the previous problem, right? If we take the grams over the molar mass, we get number of moles. And then we can take that to number of particles. But remember, over here, the number of particles that we're going to get are the number of molecules of NH3. Because we're going to divide the grams of NH3 over the molar mass of ammonia to get the number of moles of ammonia. But in one molecule of ammonia, you're going to have 3 hydrogen atoms. So in order to get the total number of hydrogen atoms, we need to multiply the number of particles of ammonia by 3. And that's going to give us number of hydrogen atoms. So if we do out the calculation here, 64.2 divided by the molar mass of this, NH3, N has a molar mass of about 14, and hydrogen has a molar mass of about 1. So molar mass is going to equal 14 plus 3, which is 17. So if we divide that by 17, we're going to get about 38, sorry. And that is, remember, that is the number of moles. Let me just write it there for clarification. Okay, so now that we have the number of moles of NH3, we can determine the number of particles of NH3 by multiplying by Avogadro's number, which is going to give us 2.27 times 10 to the 24th. But remember, that's the number of NH3 molecules, but we are asked to find the number of hydrogen molecules, so we need to multiply this number by 3. And the final answer, it's a bit crammed, times 10 to the 24. Yeah, it looks kind of messy now. But what's important is the process, because once you know the process, the calculation is really simple. We just plug stuff into a calculator. So we found the number of moles, convert that to particles, and then multiply by 3 to get the number of hydrogen atoms. And then the main takeaway is that the chemical formula tells you the number of atoms and the types of atoms. One more thing about chemical formulas is that there's really 2 types of them. The first one is an empirical formula, which is the simplest positive integer ratio of atoms. And the second one is molecular, which are the accurate proportions. And you might be wondering what this means. Well, let's take a look at an example like C6H12O6, which is the chemical formula of glucose. This is the molecular formula, because it is telling you that in one molecule of glucose, you're going to find 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. But if you notice, the ratio 6 to 12 to 6 is the same as 1 to 2 to 1. You just divide all 3 of those numbers by 6. And this is the simplest positive integer ratio of atoms. So while this is the molecular chemical formula, the empirical formula is going to be CH2O. And it follows this ratio right here, which is the simplest whole number ratio, sorry. So what empirical does is that it simplifies it. So in one molecule of glucose, you're not going to find one carbon, two hydrogen, and just one oxygen. But empirical formula simplifies everything, and it makes chemical formulas easier to deal with. All right, now we can move on to chemical equations. And chemical equations are a method of representing the chemical reaction where some reactants turn into products. So the stuff on the left-hand side are going to be the reactants, and the ones on the right-hand side are going to be products. And these chemical reactions have a specific, very important property. And it's that all the atoms on the reactant side must be present on the product side. I think my stuff here is blocking it a little. Let me just erase it. And let's see what that means, right? On the left-hand side of the chemical reaction that you see there, you have one carbon, four hydrogen, and four oxygen. And on the right-hand side, what do you know? You see one carbon, four hydrogen, and then four oxygen as well. And that is why we have the coefficients next to the chemical formulas, because we need to make sure all the atoms on the reactant side must be present on the product side. And the way you balance these is kind of just like trial and error. And so let's look at a practice problem that I put here. Let's go and see how we can balance this, right? We see that there's 6 carbons on the product side, so let's add a coefficient of 6 here to balance out the carbons. And so there's 12 hydrogens on the product side, so let's add a 6 here too. So the hydrogens are balanced, but let's count the oxygens. There's 12 oxygen on this side, and 6 oxygen, so 18 oxygens on this side. But on this side, you only have 6, and then we need to add a coefficient on the 2 to balance everything out. We're going to need 12 more oxygen, so there's going to be a 6 here. And we can check our work at the end. There's 6 carbons on the reactant side. 6 carbons, 12 hydrogens, and 12 plus 6, 18 oxygens. And then on the product side, you're going to have 6 carbons, 12 hydrogen, and also 18 oxygen. So everything balances out, and that's how we know that we've successfully balanced a chemical equation. Okay, so now that we have seen chemical equations, let's try to do some practice problems regarding the topics that we did today. Let's start with this one, which is asking us when this equation is balanced using the smallest possible integers, what is the sum of the coefficients? So this is just asking us to balance the equation basically. And let's just start somewhere, right? I'm seeing that there are 2 phosphates on the right hand side and only 1 on the left hand side, so let's add a coefficient of 2 here to balance out the phosphates. But now we have 6 NH4s on the left hand side and only 1 on the right hand, so let's add a coefficient of 6 to balance that out. Now we have 6 chlorides on the right hand side but only 2 on the left, so let's add a coefficient of 3 here to balance out the chlorides. And let's see if everything balances. So we have 6 NH4s on this side, 2 phosphates, 3 calcium, and 6 chloride on the left-hand side. And over on the right-hand side, we also have 6 NH4s. We have 2 phosphates, 3 calciums from over here. And we also have 6 chlorides. So that's balanced. We've successfully balanced this monstrous chemical equation. But that's not what the question asks us. The question asks, what is the sum of the coefficients? So let's add up the coefficients. We have 2 plus 3. And when there's no coefficient here, like over here, you kind of just assume there's an imaginary 1 there. So we add the 1 and the 6, and some basic math tells us that's 12. That's the answer. 12 is the sum of the coefficients. Great, let's move on. And this was a national exam problem. 3 different oxides of nitrogen each contain 7 grams of nitrogen and weigh 15 grams, 23 grams, and 19 grams respectively. What are their empirical formulas? Okay, so let's break it down, right, to the 3 different ones. Let's do 15, 23. Actually, let me space them out a bit more. Okay, 23 and 19. We know that all 3 of them are going to have 7 grams of nitrogen. Oh, by the way, I should point out that 3 oxides of nitrogen just mean that they're going to be in the form of NO, and the coefficients, the subscripts here could change. It could be whatever, but it's going to be in the form of NO. So let's look at each of these individually. If we know that 7 grams is going to go to nitrogen, that means that the remaining 8 grams are going to go to oxygen. So how many moles of nitrogen is in 7 grams of nitrogen? That's 0.5 moles. And how many moles of oxygen are in 8 grams? That's going to be 0.5 moles. Because remember, the molar mass of nitrogen is 14, and the molar mass of oxygen is 16. And what do you know? If we're trying to find empirical formula, and empirical formula needs to be in whole numbers, that's going to be a 1-to-1 ratio, meaning our formula is going to be N1O1, or just NO. Okay, great. Let's look at 23.0 now. So since 7 grams is to nitrogen, that's going to mean 16 grams is going to go to oxygen. So that's going to be a 0.5 mole nitrogen to 1 mole oxygen. And since we need to get rid of this fraction on the left-hand side, we can just multiply the ratio by 2 to get a 1-to-2 ratio, meaning the coefficient, the subscript, should be N1O2. And that means that's going to be NO2. And let's look at the last one. We have 7 grams of nitrogen and 12 grams of oxygen. 7 grams of nitrogen is 0.5 moles, and 12 grams is 12 divided by 16, that's about 3/4, so 0.75 moles. And if we multiply both these numbers by 4, you're going to get that it's going to be a 2-to-3 ratio, meaning the coefficients are going to be 2 and 3. And this one is 2 and 3. I don't really have space to write the answer. I guess I'll write it here. So it asks us what are the empirical formulas: NO, NO2, and N2O3. Really, what you did here was just you found the ratios, and that's what empirical formulas and just chemical formulas in general are. They're just ratios that tell us how many of one atom should there be per another atom. Okay, let's move on to, I think this is the last one, but this is the last one. Benzene C6H6 reacts with oxygen O2 to form CO2 and H2O. How much oxygen is required for the complete combustion of 1 mole of benzene? Alright, so in order to start, let's just write out the chemical formula that's going to happen here. So we're told that benzene is going to react with oxygen to form CO2 and H2O. If you notice here, the atoms, the chemical equation is not balanced, right? So let's balance it. There's 6 carbons on the left-hand side, so let's add a 6 here. We have 6 hydrogens on the left hand, so let's add a 3 here. And we need to balance the oxygen, so 6 times 2, 12, plus 3. We're going to need 15 oxygens, but if you notice here that oxygens are only going to come in denominations of 2 on the left-hand side, So the subscript would, sorry, it's kind of small. Let me just rewrite that. So it's gonna be like 15 over 2. That's gonna be the coefficient that we need to balance it out. But again, you don't want fractions, so what we can do is just multiply the whole thing by 2. So we can have 2 benzene plus 15 oxygen is going to react to form 12 carbon dioxide and 6 water. Now we're asked to find how much oxygen is required for the complete combustion of 1 mole C6H6. Complete combustion just means that like it's gonna fully react, and we know that the ratio of benzene to oxygen. So for 2 moles of benzene, you need 15 moles of oxygen, and we know that from the reactant side. The left-hand side tells us that you need 2 benzene and 15 oxygen, but we are asked to find how much O2 is required for 1 mole benzene. 1 benzene, and we can just set that as like a math equation. We can just have x O2, and if you just do the math, 15 equals 2x, x is going to equal 7.5. So you need 7.5 moles of O2 to completely combust with 1 mole of benzene. So this all ties back into like chemical equations being like this ratio or this proportion. And they tell you a lot about the reaction that's happening. They're very important, and they're going to come up a lot throughout chemistry and probably any other like field of science. So they're very important to know, and they're also really cool. I hope you learned something. That's all I have for this lesson, and I'll see you next time.